Hello, my name is Brian Dixon, and my research project is fracture mode classification in brittle rocks utilizing machine learning. For this project, our objectives are to identify characteristics of acoustic emissions radiated from fracturing in brittle rocks to train a machine learning algorithm, and then accurately predict the type of fracture and future occurrences based on the trained model. The three modes of fracture we are using are tensile, as shown by mode 1, shear, as shown by modes 2 and 3, and mixed, which is a combination of tensile and shear during fracture. The reason we want to be able to predict the fracture modes is to be able to determine in which way brittle fracture will occur. Different fracture types can lead to different failure modes, and predicting how it will fracture can help determine how to support the material in order to prevent failure. Our data was gathered from a granite specimen tested in a uniaxial loading machine. There were sensors regularly applied on either side of the sample to record the waveform of fractures which are as events in the sensors. The data gathered by the waveforms we are using has 5 characteristics which are analyzed: duration, rise time, amplitude, energy, and counts. This is recorded because each fracture mode should have unique characteristics and patterns that will allow the fracture type to be identified only from this information. The method we are using to train and predict our model is classification, a form of supervised machine learning. Supervised machine learning is a way of associating a set of parameters, like the characteristics of a feature, with a specific class of data. An example of a class would be like determining whether an animal is a cat or a dog. In the case of our experiment, it is determining what type of fracture occurs in the sample. Supervised machine learning allows us to give our waveform characteristics while labeling that set of data with the fracture type that caused it. The model is trained on a large portion of the data set, so for 70% of our data, the model was shown both the labels and characteristics. The testing data is the final 30% of our data set, and the model predicts what the fracture is based on the input characteristics. The model's accuracy is determined by comparing the predicted labels and the actual labels for the data. The model we chose to use is random forest classifier. A random forest is a collection of decision trees that process the data and then average the results between them. The way each tree works is that it starts with some data and splits the data through each branch in a way that separates the classes at the most in order to maximize organization with each step. The main problem we have encountered with our data is that it is very imbalanced. Tensile fractures make up 2,045 of the 2,607 events collected during testing, meaning that 78% of the data set belongs to a single of the 3 classes. A skewed distribution of data confuses the model and leads to inaccurate predictions, so the data needs to be balanced and processed in order to accurately make predictions. The 2 popular methods of balancing data are oversampling and undersampling, which were both utilized in attempts to balance and work through the data. If the raw data was left without any adjustment and fed into our model, the predictions would look like the confusion matrix on the left. The confusion matrix relates predicted labels, the columns, with the true labels of the data, the rows, and not only shows how many guesses were accurately produced, but shows how accurate the model was for each class. In our matrix, we label tensile fracture modes as 1, shear fracture modes as 2, and mixed fracture modes as 3. If the data was not balanced or pre-processed, the model would have a 78% accuracy by predicting almost every fracture as tensile. This needs to be fixed so that way it guesses across all classes, and there are a few steps to get there. A chart on the right shows a heat map of the relations between the characteristics and labels. A number close to 1 means that the data is very similar and has high correlation, while a number close to 0 means that the data has very little correlation. This is done with the pre-processing to help present the ways in which the model will weigh each characteristic. Because if 2 are very similar and both are treated as the same, then those characteristics will skew the data. So the data is normalized during pre-processing in order to help prevent against extremely high values skewing the data set, and data is organized so that a certain characteristic is not dominating. After processing, we need to balance the data. The first example of data balance we will be going over is oversampling. Oversampling is a method of evening out classes by generating points for the minority classes. This means that new characteristics with their respective labels are being synthesized so that the majority class is not overshadowing the minority. We use 2 modes for this, SMOTE and ADASYN. SMOTE stands for Synthetic Minority Oversampling Technique. SMOTE works by choosing a random point in a minority class and then selects k points around it, usually 5. It then randomly selects one of those points and then calculates a variable along a line between them. This is done completely randomly until the minority data sets are equal in number to the majority class. ADASYN, or adaptive synthetic, works in a very similar way. It follows the same strategy of selecting a point, selecting a neighbor, and generating a line between them. But the difference is that it does not do so randomly. Adaptive synthetic purposefully focuses on less identifiable features that are more difficult to predict and reproduces them so that the model can more easily predict these points. Something that can make a point less identifiable is that it is along the fringe of a cluster. Undersampling is a technique that balances the data by removing points from the larger classes until they have the same number of points as the minority class. In our example, we utilized random undersampling in order to balance the data. It is important to be careful using this technique with a small minority class because it can remove significant features from the majority class as well as lead to too few points to train the data on. It is important to be able to determine when to balance the data. When balancing, it can be done to adjust the training data so that the testing data is left unaltered, or it can be done to the entire data set prior to splitting it between the testing and training sets. Both can be valid in given circumstances, and it is important to be able to differentiate between them. From the models, you can see that SMOTE and ADASYN both benefit greatly from balancing the entire data set. With the entire data set balanced, our oversampling techniques maintain their accuracy between all classes rather than predicting just class 1. Undersampling underperformed in both cases with an extremely low accuracy. The likely reason is that our minority class is extremely small. It is only 232 points, which means that only a percentage of that data is being used to train our model, and that is not enough to accurately predict a trend with the amount of data we have going into it. It is also important to note, however, that our research is not complete, and what we have here is not completely indicative of what the final product will be. A reason that the data may be more accurate if the entire data set is oversampled is that the data may be overfitted. Overfitting is when a model makes overly specific grouping based on the current data set to maximize accuracy, but it makes it so that it is no longer accurate or able to be generalized to other data sets. The best way to prevent or measure this is to train the data with one data set and to test it with another. At this point, we only have one data set to work with, so there are other strategies that we need to use in order to validate the data. K-fold cross-validation is a technique that we can use to validate our findings as well as predict accuracy of a model. The way that K-fold works is it splits the training data randomly into K different groups. We use 10 in our experiment. It then trains the data on each section independently and then compares them with each other. The model used by that is then validated with the test data set. The multiple predictions and groupings help prevent overfitting. Because our research is not complete, we have other steps we are taking to try and make it as efficient and accurate as possible. A next step is to use advanced feature extraction so that we are able to have 14 and then 140 training variables rather than just 5. This can mean more nuanced differences, can be more easily recognized, and this can result in more accurate results. Other models of balancing the data are also being considered, like cost-sensitive modeling through a neural network to help weigh each class in importance rather than generating more points. The neural network can assign a cost-sensitive test by adding a more severe penalty to mislabeling a minority class, which will make a model more likely to guess it properly. Hyperparameter optimization is a method which we are implementing in order to make our current models more efficient. Each model has parameters under which it operates, so using an optimization technique allows us to set the parameters of the model to ones which yield the highest accuracy through testing multiple combinations. Generalizing the data to other data sets is another major step in which we want to work with. It will allow us to validate current data and determine accuracy of our model with an unseen data set, as well as give more data to work with. Our current progress has been submitted in a paper for the American Rock Mechanics Association for the U.S. Rock Mechanics Symposium. It is a still work in progress, but the prediction techniques for our classification models show promising results for the future. Thank you very much for listening to my presentation, and I hope that you have a great day.